Good afternoon, everyone. I'm Jiafei Duan, and today I'd like to take an opportunity to share views on my work on how do we build robotics foundation model with reasoning in the loop. So I think my vision for robotics is pretty simple. I think robots should sort of live among us, quietly, reliably, taking care of the mundane chores that drains our time and energy. So I think we often imagine this concept of a robot butler, the everyday home. But I think for decades, I think literatures and films sort of have portrayed such a future. But the question is, are we actually there yet? I think to many of us, you will agree with me as much as how impressive some of this demonstration looks like in the video. Actually, we are still pretty far away because these are all being teleoperated by human behind the scene. So the natural question that I will have in my research is, how do we sort of reach that North Star of true autonomy? I think to understand that, I think we need to look at how robotics has evolved over the past decades. I think robotics fundamentally has been really successful in assembly lines where they are pre-programmed to perform complex tasks in a very structured and controllable environment. And to deploy robots in everyday homes, I think we require a totally different kind of capability or scope of capability. So we need robots that's able to, with this kind of general purpose behavior, attribute general purpose behavior, that's trained on this kind of general purpose hardware. And one of the most common ways that we're looking into today focus on building this kind of generalist model. And this generalist model focus on scaling both data and model capacity, which we see success a lot in building large-scale language models. And a common sort of architecture has sort of crystallized within the community, whereby you have this kind of visual encoders or language encoders that takes in these observations, language instructions, and then sort of encoding it into a unified representation and train on top of this pre-trained large language model or vision language model. And the idea is to learn a tight vision language alignment by decoding the action. And as a result, it gave rise to this new class of robotics model, which is called vision language action model. I think one more noticeably we see like models such as Gemini Robotics or from Google or NVIDIA group model. But I think coming back to my North Star, I think to sort of truly achieve this kind of autonomy, I think we need to go beyond just scaling robotics foundation model. We need to be able to train our models to be able to reason before it acts in this kind of unstructured open world environment. But what does it mean to sort of reason before acting? I think humans are actually really good at doing this. And in fact, we're doing this pretty consistently. So if you look at examples of how human butler do some of these tasks. So for example, in the setting where you told them to sort of set a dining table, they're able to sort of reason in space, drawing from social norms to inform, where to act in the physical world. And that requires some for spatial reasoning. Or in the time where they try to retrieve a bottle of wine that is stored previously, for the guests, they need to be able to reason over memory, ability to sort of draw from past observations and actions to improve their next action prediction. And lastly, when they're carrying heavy objects and revolve heavy objects, in the moment you detect there's a point of failure, you need to be able to reason about what kind of failure is occurring and recover with the right strategy. So I think with today's learning paradigm, robotics foundation models are pretty capable in terms of certain aspects. They're able to perform textual manipulation, they are language conditioned, and they're able to operate all this in a reactive control manner. But I will argue that, beneath this surface level observation, there's a whole world underneath that could be empowered by reasoning capability. And this could be reasoning from the angle of spatial reasoning, temporal-episodic reasoning, and failure reasoning. And by combining this reasoning capability to enhance today's robotics foundation model, we will be able to solve some of these kind of challenging tasks to today's model, but trivial to humans. And before I sort of dive deeper into my talk, I would also like to give a bit of a definition of what I mean by reasoning. So I define reasoning. I think when you talk to different people, they have different definition of reasoning. I think more classically in robotics and AI, reasoning often refers to having a form of rational agent performing some form of explicit state space search under known transition model and reason over a sequence of states. And I think this is really good because it leverages model-based approach to sort of predict outcomes or select actions by mapping the input to output in a more structured and symbolic way. But I think in my talk today, I'll be focusing reasoning from the lens of large language model, whereby the idea is to sort of reason over unstructured information, learn intermediate steps or tokens to sort of decompose complex problems into simple ones and perform some form of later inference over this learned representation. And the output is still pretty similar. So with that perspective layout, I think my research focused on how can we build robotic intelligence with reasoning in the loop. And why does it matter? I guess it really matters because despite all this tremendous progress we see today in people trying to build this kind of large robotics foundation model, some of these models are still struggling. So for example, if you take the latest model from physical intelligence, Pi 0.5, trained with millions of trajectory, and you ask it to do a simple task, place the banana in between the two plates. And you realize that actually, it does really well at picking out the banana, it does really well at placing it, but it was never placing it in between the two plates, which is what the language instruction was specified, suggesting that this might not be a problem of lacking of data, but actually the lacking of reasoning fundamentally. And if you dive a bit deeper and look at this problem, you realize that the problem occurs even in the VLM backbone that's training some of these models. So if you take, for example, this task, which is the same task, but you only focus on in between, and you prompt some of today's frontier models and ask it to localize what does it mean to be in between the two plates. Gemini give you bounding box, Quang give you bounding box of another plate, GPT give you another bounding box. And if you use prompt engineering methods like, for example, pivots from Google DeepMind, you get an answer roughly around that ballpark, but it's not exactly what humans are looking for. So I think that precision actually matters in this case. And beyond the spatial gap, if you look at today's robotics foundation model, generalist model, in that sense, it actually struggles with temporal reasoning. So a very simple example is simulation, where you have a task to ask the robot to reopen that same drawer that's currently opened. A generalist model that's from NVIDIA, RBT2, is able to do this task perfectly, except it fails at opening the right drawer that is seen just a few seconds ago. And this is not something that is hard to understand. I think we all know that because many modern days approach are trained with this behavior cloning notion, which makes it Markovian in nature. As a result, many of today's policies are actually memoryless. And finally, I think in order for us to have robotics foundation model that can self-improve over time, you need to be able to detect failure and reason about this failure before they could come up with the right strategy to improve. But even that, today's VLM models are not even able to do that. So if you give any of these frontier model VLM, a video rollout of this task of trying to place the apple into the bowl and ask whether have the task succeeded, if not, explain to me why it fails, many of these models either hallucinates or makes a random guess, a close to 50% success rate for binary detection. Open source model basically hallucinate the way out of context from this video that was shown. So given today's limitation, I think robotics foundation model still struggles to sort of reason before it acts. And my research goal is to sort of address these gaps by incorporating reasoning in the loop to solve this problem. I approach this by doing a few things, by curating reasoning-centric data, designing new algorithms, and proposing new learning paradigms for robotics foundation model to be able to reason before they act. And for these three trusts focusing on spatial reasoning, I developed a new spatial representation that's able to ground geometry and affordance, teaching robots to know where to act. And from temporal-episodic reasoning, I draw inspiration from foundation vision-based systems to solve some of these non-Markovian tasks in robotic manipulation. And for failure reasoning, I built generalist models that's able to detect, reason, and recover from failure for some of these manipulation tasks. Let me start with the spatial reasoning problem. So for spatial reasoning, there's two reasons why Pi 0.5 could not really solve this task. I think the first reason is this ambiguity of spatial representation for action, because many of today's VLM backbones are actually pre-trained with the notion of object-centric data. They are really good at identifying objects, but they actually fail in terms of identifying non-object-centric spatial relation. So for example, in between, next to the left most, and this reasoning isn't always grounded on a single entity. And secondly, there is a huge action semantic gap where you are trying to train these kind of end-to-end models, whereby the actions can be ungrounded, which is weakly tied to its observation, as a lot of this rich knowledge from the VLM will not be able to actually affect the action prediction of the low-level part. So how do we solve this? We start off by solving to learn a spatial affordance prediction. So I think we need a VLM model that's better at spatial affordance prediction. For example, in this task. So with that, I introduced RoboPoint. And the idea of RoboPoint is really simple. Give the language instruction, this as an observation, and RoboPoint will output a list of normalized 2D coordinates. And if you try to decode this or plot it on the image itself, it points to the exact location where the language is referring to, which is in between the two plates. And with RoboPoint, we propose a new set of vision-based tasks, which focus on spatial affordance prediction as a more of a fine-grained language condition to the localization task. And the way we sort of train RoboPoint, this lies in the data. But it's really hard for you to get this kind of spatial affordance data at scale, also covering the huge amount of diversity that's required to train today's VLM models. So with that, we took inspiration from simulation, whereby we use NVIDIA scene synthesizer, generate a bunch of these kind of virtual houses, populate them with all a brew of a huge set of 3D assets. And because these are all in simulation, you're able to draw the kind of spatial relations between each object. So you are able to generate this kind of 2D annotation points as ground truth label. But what happened to those that is non-object centric points? The idea is that now once you generate this kind of object centric labels, you just need to remove the object and re-render that scene while keeping the annotation point there. And now you will have a ground truth path of non-object centric spatial relations relative to the language instruction. So with this huge data set that we actually generate programmatically, we're able to do full fine-tuning on Lava 1.5 for spatial affordance prediction. So now, given a natural language instruction, the model takes in, together with the observation that it sees, you'll output this sequence of normalized 2D coordinates to point to the exact location that the language is referring to. So what could you do with RoboPoint? So for robotics, you could obviously use it for pointing for manipulation. So previously, if you have a task that, given this current scene, you ask the robot to place the orange on the bottom stack, you might need to design some kind of heuristics to figure out where that bottom stack location refers to, or from or off-the-shelf GPT model that might not be accurate in terms of telling where the point is. So with RoboPoint, you output this sequence of normalized 2D points, and if you see on the image, it tells you exactly where it's supposed to be, which is at the bottom stack. And with a bit of the help of the depth camera, you're able to get a 3D point, and you can move the robot to that location using motion plan. But going beyond just for manipulation, we have never trained this beyond the kitchen setting, but we generalize, above that. I think the way we sort of test it is that we believe that RoboPoint is a general purpose VLM. So I did an image of me driving down a highway at Bellevue in Seattle, and I asked RoboPoint, how do I get to the carpool lane? So for those people who drive in US, the carpool lane is always on the leftmost lane. So RoboPoint will actually reply me with a natural language natural language output, telling you to go to the left of the leftmost car in this image. And then if you further from RoboPoint on the points, RoboPoint will give you those points, and if you feed it in as a video sequence rollout, you can see that the points is always consistent, predicting to the exact location where you're supposed to go. So as you could imagine, RoboPoint actually enables many capability for both manipulation and navigation. And as a result of this 2D pointing capability, we actually has been widely used by NVIDIA in terms of their Jackson hardware as one of their starting tutorial guides. And beyond that, it has been used in many today's generalist models training as the embodied reasoning data set of the choice. I think one interesting fact that we also find that RoboPoint is being used, which is to develop this kind of 2D pointing capability into these frontier models. So this is a paper that we have published. It's called Point Arena. It's basically a systematic study of visual reasoning in the form of proxy tasks of 2D pointing. And we found that many of today's frontier models before the release of RoboPoint just basically has no capability of pointing at all. And as you can clearly see, after we release RoboPoint, many of these models are able to point based on human natural language instruction, and that unlocks many ability in terms of web-based agents or agentic frameworks in some of these frontier models. But the question I have, is that,
Yeah, good question. Can you speak to the difficulty of curating the data set that you used for instruction tuning?
So the synthetic data set, so the data set is all programmatically generated, so there's not much difficulty in terms of generating that. You just need a huge amount of 3D assets, and because we're using NVIDIA scene synthesizer, it's able to sort of programmatically generate different kind of kitchen. But I think what's really interesting is that it learns the concept of this kind of spatial affordance prediction. As you can see from the example of me driving down the highway, that was never part of the data, but yet the model is able to generalize to pointing to the location that I was referring to in language.
Is there any kind of, I guess, in terms of the kinds of descriptions that people typically use? Because, it's technically true that maybe that door is behind the stable that was placed there.
Yeah.
But people don't usually use that to mean behind.
So it's based on a spatial reference.
It feels like the spatial reference bubble, and the people typically use these.
Understand, So obviously the spatial reference quality is based on the kind of data that we train with. And in this case, it's always from the camera perspective. One thing that was really interesting is that I didn't show here, which is that actually robot point is agnostic to view change. So if you're asking to point to something in between, as your camera view changes, it's always pointing in the one that's in between. So same case as if you want to point to the left of the object and you just keep changing your view, the left also start to shift. Yeah, I'll take it.
Is it fair to assume that you're limited to this curated set of relationships between so on, and also that you're also limited to certain sentence structures? For example, you couldn't say, get the apple on the tray and place it in between, like if there was two relationships in a sentence.
Yeah. So I think to the structure of the spatial relation, but we cover a huge broad range of different kind of spatial relations. But I think the second point, which is that is it to a certain sentence structure? No, that's not the case because the language is pretty ambiguous.
But if you gave it a sentence with two relationships in the sentence, what would it do?
Two relationships.
Like I said, get the apple that's on the table, place it between the cups.
Yeah, so I think in that case, we didn't try, but usually what we want to do is we have a system one, system two approach, where you have a higher model of decompose that problem down into two. Yeah. Okay, cool. Yeah, so moving on, I think obviously, you want to go beyond just pointing because besides pick and place, what else could you solve with these kind of points? So if you give a task, for example, pour me a cup of tea, and you ask robot point to solve this task, robot point will give you 2 points. And I can't think of any ways you can sort of use these 2 points in a meaningful way to pour me a cup of tea. And I think humans does this really well. Humans have a plan to guide and structure our action, where some form of implicit that to help us correct and refine our action as we are sort of rolling out these trajectories. And lastly, we are grounding this entire reasoning process of our action in the physical context of the real world. So something changed in the real world, we should be able to know. So how do we solve that? How do we build robotics foundation model that's able to sort of reason before acting? So I think existing learning paradigm of training of this robotics foundation model does not support that because we often start with initializing a VLM model that sort of converts these robot observations into tokens and aligning them with the language instruction and training them to sort of have a next token prediction objective in this auto-regressive manner. So there is no explicit reasoning before actually acting. As a result, many of these models sort of fails to brittleness towards generalization, and it sort of struggles with long horizon compositionality tasks. So how do we solve that? So I think with that, we propose this work called MolmoAct. MolmoAct is a project that I led at the Allen Institute of AI. It's one of the first few fully open sourced robotics foundation model, all the way that's open to the language model itself. So you know that every data point that was ever trained for this model. It's trained on millions amount of robot data, and it serves as a really good platform for research in robotics to sort of study some of these generalist models. And how does MolmoAct sort of solve this task? So I think unlike the other kinds of robotic foundation model, MolmoAct actually explicitly reasons before it acts. So consider this same task, given the natural language instruction and the robot observation. What MolmoAct does is that you will first predict this kind of perception token. And when you try to decode this perception token, you get a depth map of the scene. And you could actually visualize it out and see what it looks like. So that gives you some form of sense of the 3D structure of the environment. And condition on that, the model auto-reversibly create this kind of visual reasoning trace token. And interestingly, when you try to sort of decode this visual reasoning trace token, it sort of acts as a sketch trajectory on the 2D image or the robot observation. And that sort of indicates how the action should unfold forward in time. And condition on this visual reasoning trace token, then MolmoAct predicts the action that's required to actually solve this task, which is to pour me a cup of tea. So how does MolmoAct work? I think one of the main reasons that give MolmoAct its ability to reason before acting, similar to most of the LLM and VLM model of a reasoning-based model, focus on the kind of data that's used. So same case goes for us. But the problem is that robotics manipulation data is actually really hard to sort of obtain, and it's really hard to get reliable source of robot manipulation data, and collecting it from teleoperation is pretty expensive. With efforts such as OpenX embodiment, which is a large-scale aggregation of community-based effort to collect this data, we're able to have such a data set. But the problem that we found was that there is this quality and quantity issue, which is that it might not be enough and the quality might not be too good. So what we found with OpenX embodiment as we start this project is that there is data that looks like this, which has pretty low visual resolutions, or data that looks like this where there's no instructions or weird language instructions. I don't even really know what exactly the robot is doing. And for companies like Google, DeepMind, when they try to collect data for us, they had about 9 seconds of robot not moving. And if you're doing a control frequency of 20 Hz, that's the most like 200 frames of no actions. And for more modern data sets like Droid, we have robots like Grass Ting Air. So these are not the data you want to spend, you want to train a generalist model with. So the first thing we did was that we spent a huge amount of effort manually filter through all this data, and we sort of cut it all the way down to only 190,000 trajectories. And for context, the entire OpenX embodiment is about 1 million trajectory. So of course, with this 190K, it's not going to be enough to train today's generalist model. So we actually look at maybe if we can't scale them out all quantity, maybe let's focus on the quality. So we collected an in-house small cell data set about 10K robot trajectory of really diverse scenes, well calibrated, doing multiple tasks in different household settings. And even with these two data sets, we are still outnumbered by today's large generalist model, for example, Pi 0.5, which is trained on 1.2 million robot episodes. So how do we sort of outperform some of these models or even achieve a comparable performance to them? So the idea is that maybe reasoning could be the way forward. So we know that language model utilize this kind of chain of thoughts to do reasoning, but reasoning in space is really tough. Reasoning in language is ambiguous for motion in space. So I think in robotics, we need to be able to do reasoning in space. And the way we sort of do this is to curate this kind of special action chain of thought data set that can be grounded in every step. So imagine you have a trajectory of real-world robot rollouts, and then the first thing we do is we use Momo to annotate all the ripple points in this trajectory rollouts, and you can connect it together to give you this kind of visual sketch forward in time, describing what the actions should be done in the next time step. And we use that to convert it into visual reasoning trace tokens. But even with that, I don't think that's enough, because reasoning in 2D pixels is not going to be enough for 3D space. But the problem is that many of these OFC data sets, they don't have depth piece of capture in the data set itself. So we need some form of implicit depth. So the idea is that we train MolmoAct to incorporate this notion of perception token. And the way we do it is that we use that to sort of generate this kind of pseudo depth of all the robot data that we have, and we train a VQBAE architecture to extract this latent codebook, and this latent codebook then will be used to annotate as the perception token to represent some form of depth. And when you try to decode these kind of perception tokens with the decoder, you will get the depth map that was generated. And if you auto-regressively put all this together in terms of the observation, the language instructions, and then the model predicts this kind of perception token, and then followed by predicting this kind of visual reasoning trace token, and then predicting this action token, and you will get the action reasoning dataset that we use to train MolmoAct with. And of course, just with that dataset alone, it's not going to be enough. So we incorporate other multimodal web data. We also have auxiliary depth and line data to strengthen the reasoning capability of some of this depth perception prediction. And at the same time, we incorporate this thing called trajectory condition data, when the idea is that, given the observation and a sketch on the image, the model will be able to predict this action. And this unlocks the ability which we call steering for MolmoAct. And for training and inference of MolmoAct starts with initialization with Momo, which is AI2's in-house VLM model. We have 3 stages of training: pre-training, mid-training, and post-training. And the idea of post-training is to basically learn a basic action understanding and multimodal understanding. And then for mid-training, we will try to align it to this high-quality robot data that we collect in-house to sort of accustomed to the different setup that we want to test for post-training. And for post-training, we find very specific downstream data that you want to test on different embodiment. And for the way you sort of inform MolmoAct, you could do it with reasoning in space, which I've demonstrated just at the start of the video. Another way to sort of inform MolmoAct is using this notion of stability, which I will cover a bit later. And this is just a overlook in terms of how we sort of train some of these PLA models, or even in this case MolmoActs. But I think one thing I would like to really cover is the way we do tokenization. So we know that in language model, you have this kind of language text, you have a text token, and then you sort of convert it into embeddings that you want to train your model with. And for robotics, one of the most common ways people do tokenization is using bin tokenization approach from RVT2, which is the idea of turning continuous robot action into discrete bin tokens. So you have this kind of 7-DoF robot actions, and then you will first obviously clip off all the outliers, and then you will discretize them into 256 uniform bins, and then you can sort of map them either to the least used 256 tokens, or you could have special tokens that's created for this exact purpose. But something that we do that's different in MolmoAct is that our tokenization strategy differs from prior method because we want to explicitly preserve the orthogonal structure of this continuous action space. So standard discrete tokenization treats action as a categorization, categorical symbol, and sort of discard the structure that is required in terms of predicting action. So instead, we represent each action dimension using a short sequence of tokens, or more specifically, I think a string of like 3D, three Unicode escape tokens. And along that, the model is able to sort of decode them in a certain order. And this fine-grained action actually helps to sort of capture the kind of connections between the action. And we found actually this helps the model to perform much better. But the trade-off is also at the same time is that you're predicting much more action token than using beam tokenization, which makes the inference much slower. But what's particularly interesting about MolmoAct is that MolmoAct is able to sort of outperform many of today's standard VLA models and also frontier lab models on standardized pre-training benchmarks. For example, OpenAI's embodiment data. So the simpler benchmark which sort of mimics the kind of distribution that OFC has. And one thing that I really like to point out is that we're able to sort of outperform them not just at the scale of a certain amount, but we're using much less data. So for example, for Pi 0, I think they're using 39 times more data overall as compared to MolmoAct. Or for a group N1.5 uses about 26 times more data than us. And beyond that, MolmoAct is also really effective in terms of being fine-tuned for downstream tasks across different embodiments, and we outperform models like Pi 0 fast, which is another autoregressive model. But what's interesting is that we actually study how much of these reasoning tokens actually really matters. So if you try to systematically remove these kind of reasoning tokens and just focusing on predicting actions, you realize that the performance starts to drop incrementally. And one thing that we also find out by studying MolmoAct more in depth is this notion of catastrophic forgetting of semantic knowledge. So if we call it a reasoning model, it should still preserve the kind of general semantic knowledge of how do you do VQA, because like if you give an image of a dog and a cat, if you can't differentiate that, then that's going to be a huge problem. So when we did this experiment, we look at all the other VLA models together also with the VLM models that it was trained from, and we see that actually MolmoAct is able to preserve that kind of semantic knowledge even after learning how to predict actions. And an interesting feature of our MolmoAct is the ability to steer. So as I say, you can prompt MolmoAct to sort of output this kind of reasoning trace. So when you are given a natural language instruction, for example, put a toy onto the coaster. Obviously, there's 3 coasters here. So at every time step, MolmoAct will actually infer and predict this kind of visual reasoning trace, indicating where it wants to go. So the yellow line represents that. So for the last frame, it wants to go to the one at the bottom. But what I could do is I could draw on the observation with just a sketch and feed that observation into MolmoAct, and then I can sort of steer this behavior towards a different objective that I want you to sort of go towards. So I think this paradigm of training reasoning-centric robotics foundation model has, ever since inspired a line of work to sort of look into how to come up with their own intermediate representation for reasoning and explicitly embracing this kind of reason before acting paradigm. And I think more noticeably will be Google's Robotics 1.5 model. And I guess in parallel, because it's a fully open source model, whereby we release all the data and the checkpoint and also the training code, people are able to sort of easily build on top of this model to build their own generalist robotics model. So I hope that with this chapter, I'm able to sort of show that robotics foundation model must sort of reason in space to bridge the gap between semantics and action. And for the next thrust, I would like to focus on temporal-episodic reasoning, or how do we train today's generalist model to be able to reason with memory. So I think before I sort of dive deeper, I think people have different backgrounds. So I also like to formalize how most robotics foundation models today are being trained. So they are typically trained with this imitation learning paradigm, or more specifically with a behavior cloning objective or demonstration data set. So consider you have an expert demonstration data set that's collected, and the goal here is to really learn a policy to sort of minimize a supervision loss between the action predicted by the policy and the expert actions, and sort of summing up across all the time steps in the data set. And the model here, or the policy here, sort of takes in inputs, for example, the current observation. It will also take in conditional and the idea is to predict an action in return. So the observation could be RGB, voxel, point cloud per perception. Conditional could be the form of natural language, visual sketch, points, or whatever. And the action that you want to predict is more robot specific. It could be 7 log, any factor, delta A factor, or even absolute joints. So what's the problem here? So the problem here is that many today's imitation learning models are memoryless because it makes these Markovian assumptions whereby the current state is not not dependent on the past history, and as a result of this, many of today's manipulation benchmarks and models adopt these assumptions. And so the question that we have is, how do we encode memory into modern-day robotics transformer without incurring a sort of like exponential increase in computation? So how do we sort of do that? I think if you look at a problem like this, if you look at the baseline models or like a strong generalist model, for example, RBT2, we design a very simple task. So you have a task of 2 buttons, and you ask the robot to press the button that has the blue cube in front of it twice. So after the policy press that button, I remove that button from the scene, and then the policy goes and press the button again. So it clearly knows that it's here, and it has been trained with demonstrations exactly doing this task. And you guess the success rate of this task. The success rate is 50% because there's 2 buttons, the policy is capable of doing the task, but it fails to remember. But with our approach, CentOS, which I will share today, CentOS is able to do the exact same task, train on the exact same amount, the exact same data set, but it's able to achieve a success rate close to 100%. So how does CentOS do it? I think CentOS do it by solving 2 problems. First, it has to be a strong multitask behavior learning policy that's really robust. And second, it figures out the right representation to sort of store past actions and observation in a more computationally trackable way. And the way we sort of do it is through this 2-stage training paradigm for memory-centric robotic policy. But obviously, I want to sort of dive a bit deeper into how this thing works. So for the first part is that, we train CentOS, which is a multitask behavior cloning policy. And the notion is that the model takes in this point cloud as an input representation together with the language instructions. And then it sort of re-renders a set of orthogonal virtual views of the scene. And then these views are fit into a multi-view transformers. And then the objective here is to predict the next best action in the form of an action heat map from the different viewpoints. And then with this action heat map that you're predicting, you're able to sort of recombine it together to figure out a region that you should zoom in. And then once you figure out that region, you zoom into the point cloud and re-render that portion or reconstruct that part of the point cloud and re-render the orthogonal view, and you do this whole process one more time. And the 2 things that we sort of introduced into this architecture is the SAM2 image encoder. And the first thing is the SAM2 image encoder, which extracts the kind of visual features that's required to pass into the multi-view transformer. And the second contribution that we have here, which is to actually propose this new method called the multi-resolution convex upsampling, which helps to actually improve precision for solving some of these manipulation tasks. So how the multi-view resolution upsampling works is that, imagine now instead of wherever you come out from the multi-view transformer, you do a single one-time convex upsample, reshaping it into the dimension of the action heat map. Instead of doing that, you sort of break it into 3 parts, and every time when you're doing this convex upsampling, you're actually also adding in the resolution, the embedding from the SAM2 image encoder, which have different level of resolution. And the notion here is that if the model is able to perceive better, it should be able to add better. So through this kind of progressive upsampling with multi-resolution visual priors that's injected at each scale, we found that the model is actually able to do much precise robotic manipulation tasks. And the idea here is that we want to show that in the kind of tasks that we test on. So we tested it on one of the standard benchmarks in robotic manipulation, which is our bench 18 task. And we found that this multi-resolution upsampling actually has a positive impact towards high precision tasks. So for example, obviously for CentOS, we're able to outperform most of these other manipulation policies. At the same time, for very precision tasks, for example, insertion, or even for sorting shapes, we're able to actually outperform the baseline by almost 2 times the performance. And this is how it looks like. So on the left is CentOS, and on the right is the strong baseline, which is RBT2. And you can see that this task requires a model to predict close to very precise location of where you should actually drop the page for you to actually insert. And same phenomenon sort of shown in the real world example, where now CentOS versus RBT2, we want to solve a task that requires you to turn on the lamp. The model need to have that kind of very precise millimeter precision in terms of how to turn the knob, so it has to predict the right location. And beyond that, we also evaluate CentOS ability to sort of be more generalizable, or maybe in this case, I'll call it more robust to different kind of perturbation. So training on the fixed data set during training time while testing on out of distribution scenarios on this collision benchmark that I developed, whereby we programmatically change different variables, for example, lighting, textures, object size, and we found that SEM2 is actually able to retain its original performance much better as compared to other models, other baselines that's out there. And of course, in the real world, if during the same kind of task of like turning on the lamp, we introduce a distractor that has never seen during the training time, you realize that for baseline models of go for the distractor because it looks red, while SEM2 actually it will still go for the actual objective that is looking at. So with that, we're able to have a really strong multitask behavior coding policy. And then the next problem that we need to solve in this whole task space is how do you solve for the memory part? And the way we sort of solve the memory part is by building this variance of SEM2, which we call it SEM2 plus, by adapting a memory architecture for remembering past actions. So let me sort of walk through quickly on how we do this in terms of one forward pass for SEM2 plus module. So in this case, we sort of freeze the things that's important to predict action. So for example, we freeze the sample image encoder and the multi-view transformer, and then the algorithm sort of looks into sort of process a sequence of frames, keyframes, while maintaining a compact memory for each of the camera views. And this memory sort of allows the model to reason over time rather than treating each frame as independent entities. So I think to sort of begin, we sort of initialize the system by defining a number of steps that it's supposed to take and what's the maximum number of memory slots to sort of remember these keyframes and also the number of camera views. And for each view, we will actually create a memory bank, which is represented as a first in, first out memory queue. And then we sort of process, and then we sort of start this whole process whereby after predicting the actual heat map that comes out from the multi-view transformer, we actually attend together with the white spot within the memory bank with the memory attention, and then that leads to what goes into the multi-resolution assembly to predict the actual heat map, and then the prediction will be then encoded with the memory encoder and stored inside the memory bank for the next iteration to sort of draw a prompt. Obviously, the observation and the actions are being cross-attend, so when every time we sort of re-attend to predict the next actions, it draws from insights of all the past actions that's been stored in that memory bank. Now, of course, we want to test how well does this work. So one of the problems that we face is to design memory benchmarks that actually test this idea fundamentally. So we know that in manipulation or I guess in imitation learning, a lot of times when you design long and complex tasks for meditation, it might fail not because it doesn't remember, it actually might fail because of compounding error over time. So how do we test that? We look at very simple problems. So problems that we have 3 steps. And each time we actually tries to break the Markovian assumption on purpose and see whether can the model still remember its past action. So I showed one example previously. Now I'll show this second example. So in this second example, the cube could be spawned in any of these red patches. And the idea is for the robot to move this cube into the center, press the button to simulate that it's doing a different task, and then sort of come back and figure out which patch the cube originally start from. And as we compare SEM2 plus with memory and SEM2 without memory, both of them does really well in terms of solving this task. It can perform the action required to solve, but the only difference is the last step. The last step for SEM2 without the memory gets about 35%, whilst the one with the memory gets almost 100%. And the reason for why it's 35%, I think the model sort of develops some kind of intuitive bias. When you place the cube, if it's shifted slightly, it gives off a hint whether which side it most likely come from. And that's the kind of times where actually it's still able to sort of solve. As a result of this work, we actually found that there is a huge impact for today's robotics foundation model to be able to develop this kind of memory capability, and more people start to look into how they can expand bigger context window or build this kind of external memories to incorporate it together with this kind of generalist robotics policies. And of course, SEM2 is also a really good multitask behavior coding policy, which also was one of the leading policy at that year. So hopefully, I think with this style of work, I'm able to sort of convince you that the importance of enabling robotics foundation model to sort of reason with memory through this kind of memory-augmented policy learning to induce implicit temporal-episodic reasoning, allowing the model to sort of move towards a more move beyond reactive perception towards a more context-aware action prediction. And for the last line of work, I'm going to focus on failure reasoning. And I think we all agree that failures in AI has real-world consequences. I think this is especially so for robotics. So if you have a generalist policy in your house today, and you ask you to turn on the air condition by pressing on the remote button, and if it fails, the worst consequences you have is a pretty stuffy room. But what if one day you have a generalist model that's deployed in your homes and it runs into objects and it destroys the mirror and it causes harm to people? People will lose faith in robotics. So I think the question is that consequences does come for AI, especially for robotics. So we want to sort of be able to detect when these failures occurs and also mitigate these kind of failures. So the way we sort of do it is that, in robotics, people have built this kind of specialized network that's trained on very custom data to do binary failure detections. And more these days, we see methods that leverages off-the-shelf LLMs or VLMs. We just train them to look at video sequence and detect whether, have the task succeed or fail. So it has its trade-off. So obviously for the first one, it's really good at binary detection of failures, but it only works on very specific domains on custom data set. It doesn't provide you the kind of explanation that's required to sort of improve on your model. And for the second approach, it does provide you some kind of generalization to a more broader open world settings and good at binary failure detection, but it actually heavily relies on the quality of the VLM, and neither does it provide you with a good explanation of why the failure occurred. So I think we want to have a mix of everything. So we want it to be good at open world failure detection, and at the same time, we want it to be able to provide you detailed explanation of why these failures occurs. So, and one of the reasons why, in my example just now, I showed that generalist so frontier models like GPT or Gemini could not really sort of provide you the failure explanation and detection of solving this task is because it's simply not trained on failure data. So we know as roboticists, it's really easy to obtain failure as you try to roll out a policy in the real world. You just need to change the lighting slightly or introduce some kind of automation and the policy starts to fail. But the hard part to get this kind of failure data is how do you label them? So for humans, I can look at this trajectory route, provide natural language instructions, a natural language explanation to sort of generate the ground truth label. But this approach of labeling is not scalable, neither you are not able to cover a huge amount of diversity or failures in robotic manipulation. So the way I would like to propose is through this work called AHA, and the idea is very simple. You take any simulation platform that has successful demonstrations, and the kind of common failure modes in robotics, at least for different embodiments, you can sort of create this kind of failure modes. And because it's a simulation, you can sort of switch through all the different keyframes and try to inject this kind of failure modes. For example, a misaligned grass, or you move it to the right or to the left slightly. And then you try to re-simulate it in simulation. And you do this in a more programmatic way. You're able to get all this kind of failure trajectory. But the good benefit of doing this in simulation is that you're also able to get explanation in terms of exactly at which frame did this failure occurs and why it fails, because it's based on the kind of common failure modes that you have sort of listed at the very beginning. Of course, this paradigm of generative failure demonstration also has its limitations, but it actually could work for any kind of simulation that you have some form of successful demonstrations. But what's important is that now with this, we are able to sort of generate a hard failure data set. It covers a range of 79 tasks in this red domain-specific simulator, RL bench, and focus on a certain set of failure modes. And the question is that if we train this with a general purpose VLM, will we be able to generalize beyond that specific domain that it was trained on? And so that was what we did. We trained with AHA, we trained some VQA data set, we trained some localization data set on Lava 1.5 model. And the idea here is that given a sequence rollout of the trajectory, at any point in time, you could ask the model, have the task succeeded. If it's not, explain to me why it failed. And with that, obviously, it makes no sense for me to test exactly on the same domain, but we still have to do that. But the difference is that we have a hell-log test set on tasks that was not used to generate demonstrations for training. And then at the same time, we also test on a second data set, which is called Robot Fail from Stanford. And these are real-world robot trajectory that's teleoperated to fail on purpose and provides natural language explanation on why this failure occurs. And at the same time, we also want to test on a totally different domain or many scale, which is a different simulator that looks visually very different from the RL bench that we use to generate the data. And we want to see how well does the model sort of generalize across different embodiment, different domains, and different tasks. And that's what we did. So with that, we found that AHA is actually able to outperform open source and closed source VLM model in terms of first binary detection. So comparing AHA with a GPT-4o model, GPT-4o basically gets a success rate close to, I guess, like random guess, which is 50%, whereas AHA is able to hit a performance close to almost 80% in terms of binary success detection. And beyond that, we want to look at how well is the model explaining why this failure occurs. So we compare using metrics such as cosine similarity, or we also use a third-party LLM to do LLM fuzzy match to try to understand the semantic of the reasoning that's provided by these different models. And we found that AHA is actually much better in terms of explaining why these failures occur. And beyond that, AHA also able to retain the kind of general knowledge that is still preserved in the VLM model that was being trained with this new data set. And as we scale the data there's more simulation data, the performance also increases across time. So the question is, what can you do with a VLM that can detect and reason about this kind of failure behavior? So one of the things you could do is you could use it to redesign dense reward function. So I think this is a work from UPenn, which is Eureka. I really like this work, which is the very simple idea of using language model to generate dense reward functions, and you can train this kind of simulation task at scale. So the idea here is that basically you sample enough iterations of these reward functions, and you iteratively keep doing this search over and over. And this is good because at the end of the day, you will get a really good dense reward function that might get as close as possible towards solving that task. But what is interesting is that if you have a feedback loop, or you have some kind of mechanism to feedback on the reward generation. So in this case, we have AHA, given one iteration, one sample that is generated by Eureka, we can actually use the language instruction feedback of why this task failed, inject that into the next iteration generation, and introduce a penalty, in this case, because it thinks that it missed by the offset of z-axis. And in one iteration, one sample, we are able to solve Eureka for that task. And going beyond Eureka, we want to be able to show that this AHA can be used for more than just generating dense reward. So we look at open world task motion planning, whereby this work from Leslie's group, which is the idea of using language model to generate language model programs that could be used to pass into a TEM system. And the same idea of same working principle goes, we use AHA to generate natural language explanation, and we can use that natural language explanation to refine the trend that's generated by this system. And so when that passed into the TEM system, you will be able to solve that task much better. And with AHA, we also show that, I'm able to sort of push this notion of robotic failure understanding beyond binary detection towards a more interpretable and reasoned feedback paradigm. So in my further work, I also extend this idea not only just to predict failures, but able to sort of inject corrective actions, sort of bootstrapping the failure reasoning model together with an actual VLM model. So in this case, it's fail-safe is the same variance of similar to AHA. The idea is that when it detects a failure, obviously due to all these scenarios, a generalist model might not be able to recover in time. But if you bootstrap it with fail-safe, which is able to detect when that failure occurs, but at the same time predict a corrective action, which in this case is to locate the gripper, and then give control back to the VLM, to the VLA, and the VLA can continue to solve this task. And beyond that, we also develop a RobotMD, which identify how specific environmental perturbations lead to distinct failures, and this all built on top of AHA's failure diagnostic framework. And also in subsequent works, people sort of leverage the kind of failure data curation approach to generate more failure data that helps this kind of generalist model to be able to do chain of thought reasoning. So hopefully with this last piece, I'm able to sort of show that reasoning about failure is critical for robotics foundation model to sort of self-improve. And the way forward is to move beyond binary detection towards a more grounded approach and non-scalable feedback for improvement. And I think in summary, my talk today sort of showcase how we can incorporate reasoning in the loop to address some of these today's shortcomings in robotics foundation model and hopefully unlock more capabilities for today's generalist robotics model. And I think maybe I would like to take a bit of time to talk about some of my future research agenda and what is up next. So I think in my research, I sort of demonstrated that simulation plays a critical role. So for example, we have projects that looks into how can you use simulation at scale to generate semantic meaningful glass posts that you could train a glass model with. I have work that looks into how can we use large-scale simulation for learning cross-embodiment for embodied vision navigations. We are releasing this at the Allen Institute next week, which is a large-scale procedurally generated environment that covers many hundred thousands of houses that could be imported to Majoko, ISA, or any of these simulators that could be used for training robotics manipulation policies. And also, I've shown that simulation could be used to generate dynamic viewpoints that you could actually use it to train spatial reasoning in today's VLM models. The problem about simulation is that there's just some things that you can't simulate in the real world, that you can't simulate in simulation. And these are long tail events that we see in the real world. So for example, the robot falling down because the floor is slippery, or if you're driving down a really, like snowy road and suddenly a car just turns in, there's no way you can sort of simulate that, or, doing backflips, that suddenly some kind of real world perturbation occurs, you're not able to anticipate that. So I think for my next line of work, I want to look into how do we scale robotics reasoning via a world model, but not to actually learn actions from this world model. Because as you can clearly see, the world model today still have its own problems, as the context is too short, and at the same time, the kind of details that's required for robotic manipulation is simply missing. So I want to look into how can we sort of extract useful priors about potential edge cases or long-tail events that we could use to sort of do failure reasoning or to do other forms of reasoning, and also maybe to draw inspiration from some of my early work of how do we design a data collection approach that is more scalable and low cost. For example, to D2, where we collect data using augmented reality in the real world to sort of gather more robot data for very rounded scenarios that you are not able to sort of simulate. And also, I think another really interesting areas that I want to improve on is evaluation. So I think one thing that we all agree in robotics is that evaluation is not soft, and evaluation is actually a really hard problem because, real world evaluation is hard to reproduce, and as a result, people leverage on simulation as the form of doing evaluation. But guess what? If you try to evaluate some of this simulation, you realize that it saturates really fast. So for example, Libero has been used largely for VLA evaluation. In just 1 year time, the performance has hit 98.5%. So there's really no room to sort of go further. And as a result, people come up with, new evaluation that's out of distribution. So Colosseum is one of the work that I have developed, and Libero is a new work that came out that sort of tests out of distribution scenario. But I think the fundamental problem about all this evaluation is that it's still too simple, because many of these evaluation today still circles around pick and place, and which is really hard for us to gauge how well is the model truly performing this notion of reasoning before acting. So I think we need tasks that requires both dexterity and reasoning. So tasks that looks like this, which we are really capable of doing as humans. These are dexterous tasks that requires you to be able to think and reason about this kind of multi-step or even partially observable scenarios. But the point is that there is many of these tasks out there in the real world. So how do we find some of these tasks? So I'll let borrow ideas from how people do it in language model through this notion of adversarial filtering, where you are able to filter through all the simple tasks and find tasks that's really trivial to humans, but actually very difficult for models to be able to actually solve. And that will lead us to a new category of tasks that require both the dexterity and reasoning to be able to solve. And then lastly, I think folks in computer vision sort of defines this notion of dark matter, which as a metaphor for latent and invisible aspect of intelligence that is not able to be captured by a pixel level data or surface recognition, but yet governs how the scene and behaviors actually work. So I do believe that there is a notion of dark matter of reasoning for robotics foundation model. And I think in my work, I cover a few of these reasoning components. Obviously, there's more of this reasoning that we need to look into. So for example, physical property, how do you reason about physical property in the current context that is given? Or how do you leverage, force torque sensors or even tactile sensors to be able to reason about the kind of interaction or manipulation they are doing? And at the same time, look into maybe when we reach that point, there might be a shared daytime reasoning space for some of these robotics foundation models. And hopefully, I think to sort of end off today's talk, I think hopefully I've shown you that how we're able to sort of go from today's robotics foundation model towards a more reasoning-centric foundation model. And, through these iterative steps that I would like to make in my future work, eventually reaching the holy grail, which is general purpose physical intelligence. And yeah, this is my collaborators, and thank you everyone. Yeah, questions. Like,
how you perceive like text and motion planning as a perception planning control in your reasoning framework. Traditionally, people say that reasoning is like you have explicit reason. It thinks that your approach, many of ways is like essentially end to end. Yeah, reasoning is just like a modular, like integrated already. So it's like you're mixing the system 1 and system 2 together.
Yeah. So I think obviously I think the more classical approach of reasoning from the perspective of planning or this kind of model-based approach, I think it has its merit because there is some form of guarantee in the sense whereby you know there might be a solution at the end of the day. And as long as you are able to have a good estimation of the structure of the world, have a known transition model of how the world behaves, you are able to do that. Finally, a lot of the kind of reasoning I'm trying to work on, try to address problems in more of an open world scenarios where there's this kind of unstructured perception, or even you're not able to have a known model of the world. So I think that's the fundamental difference. Obviously, I think you can even think of the way that I'm doing is more loosely, whereas compared to more of like the classical approach might be more much better for the given problem they want to solve. But if you're looking at a generalized model, then you want to sort of address this kind of open world scenario, yes. Which I think there will be also a limitation for more classical here. Yes. Yeah. Oh.
Yep. Thank you for the talk. I have a questions for about hop project.
Sorry?
The hop project.
Oh yeah, fair, yeah.
Yeah. So first question is like, how do you like fine-tune your policy using the failure trajectories? Do you use cost-per guidance or use?
Okay.
Yeah. The second question is, do you do any like negative minds of those? Because for software, they're quite easy. If any random actions, those are easy, like NAC examples from policy that are to evolve. But do you do any about hard-ending learnings to like just not reach variables of what form to, or some are not? So will that help to improve the model performance?
Yes. So I think so the first question was
How to fine-tune the model.
Okay. Right. So I think the way we sort of fine-tune the policy is first standard to how you do SFT with a new data set on this kind of VLM model. So you do supervised fine-tuning, and then you basically curate this data set that in our case contains only negative examples of trajectories that fails. Contains a mixture of trajectories that succeed and also failure trajectories. And then obviously in this case, instead of giving like a kind of like a temporal reward score, we actually give an explanation or like binary detection or the like language instruction pairs of like have the task succeeded, yes or no, and then what's the explanation in terms of natural language for the model to sort of learn in a supervised way.
And you supervise using the failure tree.
Yeah.
Model will also like to give you like failure examples or.
The model will learn to be able to take in a trajectory, whether it's successful or failure, and determine whether have this task succeeded condition on the language, on the task instruction itself.
And how will you get trajectories from?
How do I get a failure trajectory?
No, how do you
Sorry, I didn't quite.
How do you get action plan?
Oh, so in this case, so for AHA, it doesn't predict action.
Just like a discriminator.
Yeah, it's just a discriminator with more non-scalable feedbacks. Yeah.
Okay, just reject negatives.
Yeah. Okay, then.
How do you do that? Do you use any correlation on that?
So in this case, we do some curation because I mean, like obviously, like if your sequence is too long, then the data set is not going to be balanced. So we actually do like a different kind of resampling of like how many frames we actually want. Yeah, in that sequence. But today, I think in today's context, if you look at some of these video models, you're able to fit in a huge context. Yeah.
Okay.
Yeah. Brain network, particularly the AHAN.
Yeah.
No, I had a problem with the first part. Because when you teach a robot spatial relations, you don't have to be exactly behind the robot. If I say from here, let's say Antonio is the robot. Say Antonio pick up the laptop that is behind the cell phone. It should be able to understand it because if it can build a representation in what we call allocentric system, your representation though is always from the camera of the robot.
Yeah, for the camera.
For cameras, the case of Phi Zero are cameras which are randomly placed,
Sure.
right? So there is that's very limited. I mean, you cannot because we don't know where the camera will.
I see.
Even if the camera is on the robot, always on the head like a humanoid, you cannot expect from a human to explain that from the point of view of the human.
Or is from the point of the camera.
Yeah.
Right. Yeah. So
We never expect, in particular, because we showed so complicated the spatial relations.
yeah.
I mean, they really look like a puzzle, right?
Yeah.
I mean, you can't expect a human, this is from the left of Antonio, and this is with respect to Antonio is from the right.
I see. So that's something that we are not able to sort of incorporate the kind of coordinate system from the different perspective. But I think the notion here is that I think it's agnostic to where you place the camera, because when we generate the data, we are actually perturbating different viewpoints in terms of where the camera is generated. So obviously, if I'm generating the camera, I'm generating the data from this viewpoint, then the left could mean different as it's generated from a different viewpoint. So that's something that we actually want the model to inherently learn from the huge amount of data that actually generates.
Put the words in your mouth, but from at least the results that you showed to the content you're given, you seem to not believe much in end-to-end training, images to action. You believe in intermediate representation. So the point and the 3D and the plan and this and then that and the failure of the function. So is my understanding correct? That is one, yes, no, and why? All right, so you go ahead.
Yeah, so that's a good thing. So I think I used that slide which I removed, which basically looks at today's. I think the foundation model of robotics is kind of loosely defined, but I guess like more this kind of generalist manipulation policies or models. And if you think about it, there's many three tracks, and these three tracks are end-to-end approach, which is what you just described, going from observation to action. There's another track which is more of like a modular approach, where you have all these different API calls, and you're able to sort of call these different APIs, and you're able to get this different perception, how to grasp and piecing these parts together with like a high level planner. And then there's a third approach, which is hierarchical. And that's something that my advisor did sort of propose as a hierarchical VLA, whereby the notion is you have I guess people call it system 1, system 2, but his way of doing it is more of like having a high level model that's able to output intermediate representation, but you don't train the low level together with the high level. You sort of have a low level policy that's just trained on conditioning on the intermediate representation. So in that sense, these two are still decoupled. But the problem about that approach, which I found, is that if you're doing this, separate training, there is a possibility that actually is unbalanced, which is that the low level policies are actually not as powerful as the high level model that's able to output this kind of intermediate representation. And that's something that we actually compare in MolmoAct, whereby we found that if you do an end-to-end approach and still having this concept of intermediate representation, somehow it actually was much better than the hierarchical approach. And I think the notion of the hierarchical approach is to be able to enable more robustness or generalization towards the policy, because now you are decoupling the high level, understanding of what is the apple and what's the pear, how do you sort of go towards that and sort of represent all this in the intermediate interface, and then having a low level action just following the intermediate interface as faithful as possible. But we found that actually if you train in this end-to-end with that intermediate interface being sort of integrated into the training paradigm, we found that actually the connection is much more tightly aligned, in the sense whereby now you're able to better control the policy to say, okay, I'm going to the left, but going to the left, what does it mean? It generates this kind of intermediate trace, and then condition on this intermediate trace, then the model predicts the action that sort of steer it towards the objective. Yeah.
We're a few minutes past, so let's say one more question, and then and bring things off on Ayla. It can follow up on this question. I think it sounds like your approach is like building some spurious correlations between like
your reasoning chain and also the action. But like as Kostas mentioned, like if you change your waypoint, your spiral creation could be break because like your navigation is assumption for some like specific viewpoint. Even though you train on different viewpoints, it doesn't necessarily mean that you actually learned the correlation between your like reasoning with text. Targets. In short, like in the future world, like to be able to like actually learn like our arguments research implicitly. We don't call through like one code. We don't anything.
Sure. I agree. So I think how do we ensure that? I think there is something that we did with MolmoAct that tries to ensure this. So I think in previous method, if you do end to end, it's a black box. You don't really know why suddenly the action doesn't match the language that you give. You're correct. The way we sort of design this kind of chain of thought process, we make sure that every part of this can be decoded. And if you are able to sort of decode it, you're able to sort of diagnose, correct? In the sense whereby if you look at the kind of visual sketch, if the visual sketch is totally away from, if it's going to the right as your language says to go to the left, then you know the policy is going to fail. So that kind of interpretability was sort of built into this because we made this kind of intermediate process able to be grounded and able to sort of decode. And then, the interpretability, I think, is sort of what was like a safe mechanism in this whole system that allows us to sort of diagnose this as a scenario. Obviously, it's not good enough. So I think my point here is that I don't really know. Is it because if let's say we scale more data, will it be better? Or what is the other missing piece? So also another thing I want to point out is that right now we are doing a lot of my work is focusing on reasoning from a more of a data-centric approach. If you think about it, it's reasoning on the output space, on the token level. But what does reasoning looks like for representation? I think that's something that we're also exploring. Yeah. Great. Thank you.
Great. So that was things we go over.